So thank you to everyone to be here today. Today is a special day for sCO2-flex project because we just finished our final meeting 2 years ago, today 2 hours ago, sorry. And we are really enjoyed to present, to make this public workshop with you. We are very sorry to not be able to make this workshop in presence, face-to-face, but due to the health situation, now we are used for these Teams event and Zoom event, so it will be okay. So the main idea today was to invite main project funded by the European Commission and dealing with the supercritical CO2 cycle in order to show to everyone and to present you a part of this activity in Europe and to show that this topic is a very interesting and very dynamic, especially in Europe, and not also on some other projects like you can hear in US and in Asia. So first we will have a presentation by Eric Leconte from the European Commission, and after we will go on the several project presentation. So the format will be to have each presenter will have 15 minutes of presentation, and you will be able to speak and to ask your question during 5 minutes after. Okay, so if it's okay for you, I can propose that you will switch the camera off, not for the person who will present. And I think the floor is yours, Eric.
Okay, good afternoon. So let me share my screen, my presentation. So, yeah. Sorry. Okay, all right. So do you see the introductory slide, the cover sheet? Yeah.
Yeah.
Okay, all right. Yeah. All right. So it's my pleasure. So thank you for inviting me to this joint event where, as I understood, 5 projects will present their progress and results in dealing with supercritical CO2, and so it's my pleasure to give some introduction. And so, yeah, I'm trying to go to the next slide. Yeah. Okay. All right. So this is the graph showing the global CO2 emissions, and you see indeed that there was a small dip because of the COVID crisis, of course. But in the following slide, you also see the now the accumulated CO2 concentration. And there you can see that it's hardly visible that in 2019 or 2020 there was any change in concentration, and definitely compared to the pre-industrial concentrations around 280, we are now above 400 ppm, so and still growing. And also global warming is a reality already today. This is the graph of the temperature difference, 2020 compared to an average from 81 to 2010. And you see that in some areas it's even 5 or 7 degrees of temperature increase. So it's really a severe situation that we are in, and in the future we can foresee also consequences of that in terms, for instance, here is in terms of water scarcity and water stress. So you see all those areas and water scarcity and stress means that there is a potential migration of populations from those areas, so where they cannot grow their crops anymore, to other areas. And so the immigration that we have known in Europe, totaling maybe 1.5 million, which is much less than 1% of the total population of 450 million. This immigration that we have known in the past years could be multiplied by 10 or 100 in the future. So it's a real issue that is touching everybody around the world and in particular Europe. And so, of course, you know about the Paris Agreement. So we, as Europeans, can be very proud about it, that we are really leaders in terms of fighting the climate change. And as you know, United States was not following us for a few years, but now coming back strongly. And we have now also Japan, China, and other countries announcing climate neutrality objectives in the future. So this is encouraging. Why is it needed also to go stronger? Is that presently from the COP21, COP15, sorry, in 2015. No, COP21 in 2015 in Paris, there were those nationally determined contributions. So and that's referring to the blue curve you see here. So if every country lives to the promises made in 2015, this will be the situation of CO2 emissions. So it will just level around 50 gigaton per year. And so it's not at all a trajectory that leads to 2 degree or 1.5 degree, but it's rather, you can see on the right, a temperature rise up to 3 degrees by the end of the century, but not even leveling. Whereas the other trajectories with 2 degrees or 1.5, there you see it stabilizing. And that's, of course, the reason why the Green Deal was put in place. And what is important to know is that the Green Deal is not only about fighting climate change. It's really doing that in a way that it's a growth strategy for Europe. So taking advantage of this change, taking the opportunities for European economy and industry to be a leader in technologies, and so to be able to sell those technologies and so generate activity and create jobs in Europe. And you see it's also a very comprehensive strategy looking at, you see at top left, climate, then energy just below, of course, the biggest contribution to climate change and emissions being energy production and energy use. But also industry with more circular economy, building and renovating, so reducing the energy consumption in buildings. And then on the right, you see also that it's not only the climate, but also more globally the environment with the air pollution, also the protecting biodiversity, and looking at the comprehensive food chain, and finally, of course, the way we move. And then if we focus on energy, what came out of that is national energy and climate plans, because the Commission cannot do that alone. It's, of course, the member states that have to put plans in place to reach those objectives by 2030 or 2050. Also revision of the directives for renewables, for energy efficiency. This is ongoing now. and a strategy for offshore wind, hydrogen. This was already published in 2020. And then now preparing the revision of the 10E, so Trans-European Network Energy Regulation, and having launched the renovation wave strategy in 2020. So this is really what we are busy with in DG Energy, in particular, all those activities. And on top of that, I could also add the recovery plan, which was not foreseen at the beginning of the launch of the Green Deal, of course, because COVID was not yet there, but definitely the recovery and resilience plan, of which 37% at least should be dedicated to fighting climate change, is one of the substantial financial mechanism to make sure that this happens, and that also it's happening in a just transition way, leaving nobody behind. And then, so that was a strategy for 2050, but in order to reach the climate neutrality in 2050, you see that the line, if you draw a line in between the 55% reduction by 2030, is certainly not going too quickly. So that's why there is now this 2030 climate target plan, so with a higher ambition in terms of reduction of greenhouse gas emissions. And so indeed, this target of minus 55% compared to 1990 that was proposed by the Commission. And now being the plan to reach that being devised. And more precisely, what is this climate target plan? So it's now putting up scenarios. So how, not only what we want to achieve, but how we will achieve that. So, and so there are several scenarios, 5 in total. The first one is looking at how the regulation can be stronger to reach the target. So directive regulations, standards imposed. That's in the blue box. Circled with red, you see the carbon price. So really rather using then regulations using a market tool to reduce the emissions. So that means increasing the carbon price, but rather also increasing the scope of the emission trading system. And indeed, the enlarging the ETS scope to not only what we have today already, power industry and intra-European aviation and navigation, so to expand it to road transport and buildings. And then, so these are two scenarios. Then the mixed scenario is a mix of the two that I've just talked about before. And then there were two scenarios, one looking at 55%, one at 50% target, in case there would be some negotiations in between. So that was the idea. And so one of the consequences of this policy, notably on carbon pricing, is probably you are looking at the price of 1 ton of CO2, so the allowances on the emission trading system market. So meaning that beyond the free allowances, the industries that emit beyond that threshold have to pay that amount for each ton of CO2 that is emitted. And you see that after a long period with very low levels, around €5 per ton, it went up the last couple of years to around 25 ton, and now recently has risen to 50 is now stabilizing around 50 euro per ton. Why is that? Is that because in 2018 there was a revision of the ETS directive, reducing increasing the rate of decrease of free allowances. So the free pot decreasing, the more the industry has to buy allowances to emit, and so that pushes the price up. And then more recently, that can be an anticipation of higher CO2 prices following the higher ambition 55%. And so indeed, this is a table, but I will not go into the details. You see that for those scenarios, each time the assumptions were analyzed, and also, most importantly, the impact of those changes. And for ETS, it's also including, of course, the international aspects. So pushing with international diplomacy to enlarge the scope of ETS, and notably for aviation within the instruments like CORSIA, which is at worldwide level. And yeah, I also wanted to talk about the energy system integration, because I think it's relevant for you. The strategy. So you know that in the past it was rather linear. Oil for transport, linearly coal for industry, gas for industry and heating buildings, and electricity produced from various sources to all the sectors. But now more and more, as you know, with the growing share of renewables, which are variable, then indeed everything is much more will become much more interlinked, in that in order to cope with the variations of the renewables, storing this energy, converting this energy into new energy vectors like hydrogen, are really the solutions to have an integrating system. And so why does it need to be integrated? It's because the optimization at global level, at system level, will make it cheaper than just adjusting sector by sector. And so coming now back to what is really of interest for today, the supercritical CO2 cycles. So definitely the closed cycles for recovering industrial excess heat or waste heat, as it's usually called, and converting it back to power, mechanical, electrical power, is certainly very relevant as the system integration will go together with more electrification of industry. And so industry being a bigger user of electricity will be in a good position, will be incentivized to also produce electricity from the waste heat, so that it can reduce the bill, the electricity bill. Maybe also an incentive to store the heat before converting it, in order to convert back to electricity at times when it is interesting, of course. So it means when there is not an excess of or an abundance of renewable electricity production, but rather than, of course, during the when there is no sun in the night, or when it's cloudy, when there is no wind. So a storage can help to produce the power at the right time. And that's why we, in addition to programs like in the last work program of Horizon 2020 on supercritical CO2, we also have topics about energy storage and thermal energy storage for industry at higher temperatures. Another application, but that you know better than I do, of the closed cycle is to generate power. So when heat comes not from recovery, but rather from original generation. And then finally, this is not so much linked to the projects that are running now, but still linked to supercritical CO2, the Alam-Fedvet cycle, where after separating oxygen out of the air to have oxy-fuel combustion, and so a very high concentration of CO2, it can be recycled in a semi-closed cycle to operate in supercritical and have a very good efficiency of the turbine, and with the advantage of recovering useful outputs out of the air like nitrogen, argon, and also that's at the input, and at the output, of course, a CO2, well, exhaust gases that are at very high level concentration of CO2, so easier then to capture and eventually to store. I see that Gustavo has appeared, which is a sign that I've exceeded my time limit. And so that's it. So thank you very much for your attention, and I'm open for questions.
Thank you. Yes, we have maybe time for 1 or 2 questions. If anybody would like to intervene, please do so vocally, or if you prefer via the chat, and I can also bring them up via the chat.
Yeah, Eric, maybe I have a question, because you mentioned the Alam cycle in your last slide, and as you say, for the moment there is no European project about Alam cycle. I think that maybe it's because until now the different call for funding were not to say oriented in order to reply with Alam cycle, but do you really think that it could be a good conversion cycle in order to use it for the next gas plant generation? Because one of the main advantages of the Alam cycle is to be used with a gas plant and to be able to produce some CO2, but to capture the CO2 as it's produced.
Mm-hmm. Yeah. So I think there are 2 elements in my answer. The first one is yes, there is this advantage of producing concentrated CO2. So it seems to me, but you are the specialist of turbines, of course, and power plants. It seems to me that compared to a CCGT plant, followed by CO2 capture, but which means also concentration of CO2, because CCGT uses air, so there is a lot of nitrogen in the exhaust gases. So I see definitely an advantage there. On the other hand, it's definitely sticking to natural gas. So definitely it doesn't go along with the switch to more hydrogen or even 100% hydrogen in as a fuel for the gas turbine, because then it has no interest anymore, of course. So that's why I don't think there will be any European support for the Alam-Fedvet cycle, because as you know, the priority in the funding is in renewable energy sources and not in the perpetuation of using natural gas in the power production.
It's
so
okay
yeah.
We won't have to prepare a proposal with alarm cycle. It's okay for me.
Yeah, and yeah, already in the past, you know, the supercritical CO2 cycle was funded because it was meant to be used for waste heat recovery. This is in line with the energy policies of energy efficiency, whereas when it's really for generation, power generation from natural gas, it doesn't go along the lines of decarbonization of electricity production and going to more renewables and less fossil fuels. Yeah.
Okay, I think we should probably move to the next presentation just to keep time. Sure. Thank you very much.
It was my pleasure. Thank you. So I switch off my camera. Yeah.
So if I remember, Gustavo, the next presentation is mine?
That is correct, yes.
Okay. Which one?
Your sCO2-flex results.
Yes, okay,
yeah.
it's perfect. So thank you. Okay, so I will present to you the sCO2-flex project. sCO2-flex project, just to remind the context, we finished at the end of the month. So I will really enjoy to present final results with final numbers. So today, and just to precise, because as you will see, at the beginning, the proposal for sCO2-flex was made 5 years ago, yes, and the context of energy mix was not the same. So I think that now, if we will make a new proposal like for this project, maybe we will orient the project on one other type of fuel, but all the results presented today will be applicable, and it's one of the deliverables of the project could be applicable in the other application. So I will check. Okay, so what is sCO2-flex? So sCO2-flex means supercritical CO2 cycle for the flexible power cycle. So our aim was to, at the beginning of the project, to validate the design of a 25 megawatt Brayton cycle, so a closed cycle, but not as the alarm cycle, using a new fluid, instead of the steam, we will want to use a supercritical CO2. And the idea was to show that this type of cycle can really increase the operational flexibility for the conventional thermal plant. So we have main objective. It was to show that we improve the flexibility and the efficiency for the cycle. And we also decrease the greenhouse emission, especially for solid fuel, because sCO2-flex was based on a solid fuel cycle. And also we can decrease or be similar for the cost. So our consortium is really equilibrated because we have some academics partners like University of Duisburg-Essen, University of Stuttgart, Politecnico di Milano. We also have some research institute like UGV, Severec in Czech Republic, but also CSM RINA in Roma, specialized in materials. And we have some industrial for the main equipment of the project and the cycle, so FIVs for the heat exchanger, and Baker Hughes for all the turbo machinery. EDF is a coordinator, and we integrate, we have the roles of main integrator of the cycle, and thanks also to Gustavo and Zabala for all the work done during the past years. So at the beginning of Flex, we have some very high challenge. First, it was to develop a boiler for a solid fuel, because we want at the beginning to show that we can gain a lot of flexibility for this type of fuel. We also have to develop some turbo machinery, so compressor and turbine, really dedicated to supercritical CO2, and to want to test the compressor during the project. We also have to develop some heat exchanger, very compact heat exchanger, so high temperature and low temperature heat exchanger. And all these developments, this challenge were also with two big questions. First was, okay, what we could use as materials in order to, because we already know that materials will be a very big challenge for the project and for the cycle, especially for the cost and the reliability of the cycle after years and years of operation, and also for the flexibility, because we decide not to use the current flexibility operating strategy we have in the current steam plant, but to start from zero and to think a new strategy, maybe not so new, but just to start from scratch and to be able to say, okay, we forget what we know and we will see what we can do in order to be as flexible as possible. So now, 3.5 years after, and COVID lockdown after, we have very good results. We will be able to develop a new design of turbine. It was a mechanical design with a 5-stage turbine with a good efficiency, which is around 88% of isentropic efficiency. We also provide, and thanks to Baker Hughes for this work, a 5.4 megawatt prototype of a compressor with a dry gas seal system. We were able to test it in a new test bench, so a new supercritical CO2 test bench in Baker Hughes factory. So we can test it from 100% to 20% load. So we want to reach all the different, all the range of part load and full load of operation for this type of equipment, and to test it in different operation. We provide also, thanks to FIV, several prototypes for two types of heat exchanger. So one printed circuit heat exchanger and plated fins heat exchanger. These heat exchangers were tested on two other facilities, sCO2 facilities. So one in Stuttgart, in University of Stuttgart, and one in Severage facilities. And for this type of heat exchanger, we also increase some resistance, because for the PFHE, we will be able to reach more than 1,200 bars of pressure test, which is very important because at the beginning of the project, we cannot reach this pressure test. So it's one of the success of the project. And after we developed also a design for a boiler dedicated to solid fuel. So our cycle will run around 620 degrees with a high efficiency, 92% of efficiency. It's quite interesting because until now, there is some design of boiler dedicated for sCO2 cycle in the literature, but many of these designs were just retrofit on the current boiler. So now we work with UGV, work a lot in order to provide a good design with good perspective for all this equipment, about materials, because we also made a lot of tests in CSM for the materials. So We also, and I think it's one of the most important achievements of the project, about the equipment, which are very important too. We really realized an engineering design as if the plant was real and concrete for us, and as if we have to build this plant as operator of this plant. So what we noticed, you can see a screenshot of what could be the implementation of the plant, is that we have a very compact design for a plant. This is a design for a 25 megawatt cycle, but it's very compact. The reduced footprint was also a lot, with a lot of reduction. We will able to manage, okay, new type of building, because we see, okay, the plant is so small, so maybe a very concrete building is not necessary. We can think about new type of building, and this work is very important because in this design we take account of every auxiliary equipment we can have in the plant, and the work was performed by an engineering team, so a team who will build this type of plant or who operate this type of plant every day. So they really take account about the needs of an operator, a plant operator. We also work a lot on the flexibility and to understand the operation of the cycle. So the plant operation was, as I say, with a really new strategy. So in order to understand the off design and to be able to modelize the dynamic performance of the cycle, we test several operating strategies, and we choose one which is mixing different strategies. So first, we have a slide pressure for the turbo machinery, which is a current strategy in a actual plant. We also have some variable speed fans for the heat rejection unit. And we work with a supercritical CO2 inventory in order to set the cycle minimum pressure. And what we see is that if we have we try to be in a part load of 20% of part load, which is very low and could be a very low load asked by the different network operator if we don't want to stop the plant, is that we have an overall efficiency very good and better than the current plant, solid fuel conventional plant, because we reach almost 30% of efficiency for the plant. So it's very good, and we show that the plant is very flexible because we can have a very high, very quick increase and decrease of the load of the plant. And it's also, and it was very important for us, totally compatible with primary frequency control on the grid. This means that if tomorrow we build this plant as we design it and as we prepare the operating strategy, it will be compatible with frequency control on the grid. So it will also be easier to integrate it on the grid by the different network operators. And because it was very important to see if this plant are quite new, are quite efficient, are quite flexible, but also, as it's still conventional thermal plant, we need to see if we can address some environmental impact with the project. So what we proceed to a life cycle assessment and to several studies about social acceptance and to prepare maybe standardization question about this type of cycle. So what we saw is that we have a lower environmental impact than the reference plant in operation, where we have 8% less, this impact is 8% lower than the current impact. And if we think about the overall during the overall lifetime of the plant, we are still lower than the current conventional plant. We are almost we are around 5% less than the conventional plant. As I said before, with a screenshot of the design of the engineering design, we have a very good reduced footprint, more than 40% of it. Also, as we reduce the size of the materials and the equipment, we reduce the cost, we reduce the tonnage. So the different needs for concrete, for some metals, some nickel alloys, for example, or other alloys. And we also provide during the project some studies in order to be able to provide a social code for conduct this research in the field of energy. It was very important because we know, and every day everyone listens that this type of plant could be very difficult to be accepted, especially with this new working fleet. We could be a little bit we could happen with a lot of questions for the society. So it was very important for us to work on this type. And maybe one of the main results is it's also the cost. We made two estimations. We made an estimation for the 25 megawatt and also for a 105 megawatt cycle. So what we see is that if we want to build 25 megawatt, we are under 100 million euro, as we expected at the beginning of the project. And there is a very big margin of reduction because the boiler, so a conventional solid fuel boiler, is almost 30% of the cost of the overall plant. So if we decide to build a 25 megawatt plant without this type of boiler, without this type of fuel, but one other fuel, it could be very interesting because we will be around the 70 million euro. There is other 70 million euro, yes. And there is other margin of reduction because we as the work was provided by an engineering team, so some people who have to deal with real plant, we take a very conservative margin about some other costs like the engineering cost, assurance cost, and we know that we can reduce again the price. And what it's really important too is that if we go on a 100 megawatt plant, so 4 times the power of our current design, we are not 4 times higher, but just only 2 or 2.5 times higher. So what is the next step in the project? The project is almost finished, but there is a very good perspective in order to think and to see what we can do for this type of cycle. I think, and all my team thinks too, that there is some improvement for the equipment which are possible. Turbine and compressor efficiency could be also again improved and better understood for the flexibility. The heat exchanger design could be also improve in order to go to higher pressure. And also, as I say, this design was maybe at the beginning designed for a conventional plant, but we think that the cycle without the boiler could be used for other applications. So solar, concentrated solar, biomass, heat recovery, or retrofit on existing plant. And I think that also, which could be very interesting, is that to continue to study the operation and the efficiency with maybe different cooler system. In our design, we take a classical water cooler system, but we know that in some area of the world where the water is very, it's a raw product and very expensive, some cooler system with a hair dry system could be very interesting. And if we choose this type of cooler system, there is still some margin in order to improve the efficiency of the plant. And that's all for me. Thank you very much.
Thank you, Albani. We are, well, slightly delayed, but that's fine.
I'm
started
sorry,
a little bit
I don't
later.
see you when I present. I'm sorry.
No worries, no worries. If we have, if anybody has one or two quick questions now, otherwise we can also save them for the end as well. I don't see anybody in the chat posting, so if there's no question, then I will welcome David to present the Scarabeus project, or actually no, jump out of then. Sorry.
Thank you very much. And thank you very much, the sCO2-flex project, for inviting me for this presentation. I'll share the screen. Okay, here we go. I set the time just to make sure I stay in the 15 minutes. So I'm here to talk about the Scarabeus project, which stands for Supercritical Carbon Dioxide Alternative Fluids Blends. So the concept word is blends, for efficiency upgrade of solar power plants. So if you want to start from the title of the project, the two key parameters or aspects are blends and solar power plants. Actually, the objective and the aim of Scarabeus is to develop and demonstrate supercritical CO2 blends for CSP applications, because CSP applications have the peculiarity of not having water, or if you have water for heat rejection, it's rather expensive. And the second point is about the high ambient temperature, which can negatively affect conventional supercritical CO2 cycles. Performance and KPIs are in terms of CAPEX and OPEX reduction. And here in this picture, we try to summarize what are the advantages of the CO2 blends when applied to CSP plant. We expect to have high performance via conventional steam cycle, which is the reference case, smaller turbo machinery, fewer equipment, and specifically develop a condenser in order to tackle the issues of the arid situations, as well as working with blends. The consortium is here reported. We have 5 universities working on the project: University of City London, Politecnico Milano, Technical University of Vienna, University of Sevilla, and University of Brescia. We have 1 SME, which is Quantis, and 3 large companies as Abengoa, Kelvin, and Baker Hughes. So as stated, the concept is to add small quantities of select compounds to the pure CO2 so that condensation can occur even at temperature of 50 degrees to 60 degrees C. Meaning that even when you have ambient temperature of 35, 40 degrees C and you have air-cooled condenser, still you can have a condensing cycle in the power plant. The advantage in terms of simpler cycle and small turbo machinery is the same as having supercritical CO2. So from this point of view, there is no relevant difference between using blends and pure CO2. Here in a nutshell, we have some timeline of the project. It started around 2 years ago. And then in December 2020, so around 6 months ago, we identified the most promising blends that are selected in around 2 weeks' time or a little bit more for the demonstration in terms of both efficiency and cost target. We expect that in September 2022, there's going to be the inauguration of the test rig and the CO2 blend testing will start. And hopefully by the end of the project, we'll demonstrate the technology and the concept, both from efficiency perspective and economics perspective, which is calculated through simulation tools, as from the experiment at VM. In the following slide, I will describe the main aspects identified as critical, how we approached, and the main results so far. Please consider that we are roughly halfway through the project, considering that the last 14 months were strongly affected by the current sanitary situation. The fluid identification approach is the first key aspect tackled in the project, which objective is to identify the most promising fluid, to assess the thermodynamic properties of the blend CO2, and demonstrate the stability up to 700 degrees C. As last demonstration step, the CO2 blend shall be stable for 2000 hours at the selected temperature. How to identify the most interesting blends? We have a parallel approach. First, we develop, once identified the most promising candidate, vapor equilibrium tests are carried out. So to calibrate equation of state with experimental data. And in this case, there is the objective to identify the critical mixture behavior and the thermodynamic properties. On the bottom part, there is the stability test, where in principle, we aim to develop CO2 blends which are stable up to 700 degrees C, and this is determined using the measurement deviation in the isochoric lines. So this is the kind of approach we use for identifying the most suitable fluid, and here are some preliminary results. So we started with looking at literature data to select what are the most promising fluid, and in the first year we identified 5 dopants. 2 more were identified in the second year, and once selected this dopant, there is already preliminary screening, like looking at thermal stability or critical temperature, or looking at the chemical stability in terms of whether the fluid is reactive or not against air or water. And this preliminary selection identifies what are the dopants to go for experimental tests. So first of all, the thermodynamic assessment is performed through Peng-Robinson equation using binary interaction parameters from literature data, and then VLE tests are performed. And in particular, we perform VLE measurements for 2 dopants. So the idea is to determine the bubble and the dew line of the fluid, so to calibrate the equation of state. And here is, on the contrary, the results for the thermal stability test at UniBS. So far, we did measurements for 2 blends in terms of VLE and 3 blends for thermal stability, together with measurements performed for the CO2, which, even though it's stable, it has some interactions with some stainless steel materials, so this was investigated as well. As of today, we identified 1 dopant, which is stable above 550 degrees C, and is suitable for CSP multi-zone application. Certainly is lower the target of the project, which is 700 degrees C, but still it's promising, as this fluid could potentially be applied to the current technology of CSP plant. And so this is the approach and the preliminary results about the fluid identification methodology and procedure. The second part of the plant which is investigated is about the turbo machinery design, to see whether the CO2 blends affect the design of the turbine, how to select the pump, and the mechanical analysis performed by KUX in terms of design of the turbine. From this point of view, it's an iterative approach, because the blends has to be identified, optimize the concentration, and then according to the selected concentration, the design of the turbine starts, and then back and forth until the final and optimal configuration is identified. So far, it is, as preliminary results from this activity, it is quantified the effect of dopant molar fraction on turbine design. It is assessed that certainly the uncertainty in the thermophysical properties, which still is present in some of these, affect the turbine design and how it affects. It has been validated an axial turbine mean line tool, developed a flow path design for candidate mixture, and validated against CFT. The preliminary results, so you see how adopting blend 1, blend 2, blend 3, which changes in terms of molar molecular weight and properties and so on, the turbine efficiency characteristics change significantly in terms of mean diameter as well as blade age. And as well, it is also, in this case, performed the preliminary design of the the turbine with, in this particular case, the relative Mach number is indicated for each stage of the turbine. Moving to the heat exchanger, the heat exchanger focuses on two different heat exchangers. The first one is the air-cooled condenser, which has to deal with the CO2 blend in condensing phase and with high ambient temperature, and the recuperative heat exchanger for the cycle, which both have to deal with the blended CO2. So both are specifically designed for the blended CO2. In particular, Kelvion will perform the design and manufacturing of the recuperative heat exchanger and air-cooled design for the testing, so at the pilot plant in Vienna, but they will perform also design and cost assessment for the large-scale recuperative heat exchanger and air-cooled condenser. So the first one is about demonstrating the technology, the second one is to see how it will look like in large-scale plant. So far, this activity was quite affected by the sanitary situation. There was the first modification of the test rig, developing and designing all the main components. Heat transfer correlations for pure CO2 and a blend zero. It's called zero because it's supposed to mimic the final blend behavior. Measurements are performed and the safety simulation are as well carried out in order to design properly the heat exchangers. The recuperator 1 is designed and now currently under construction, and about the print circuit exchanger, the diffusion bonding testing are about to finish and they will set some conditions for the design of the heat exchangers. Then we have the activity which is about techno-economic environmental analysis and approach, and this work package or activity is just numerical, so simulation based, and it will demonstrate the targeted cost of the project, which are here reported. In addition, there is the environmental impact developed through the life cycle assessment, and also a social impact is evaluated within this work package. So far, it is developed the state-of-the-art CSP plant with central receivers, and the thermodynamic analysis of closed cycle using CO2-based fluids. From the modeling point of view, it was demonstrated that CO2 blends can achieve an efficiency above 50%, assuming 35 degrees C ambient temperature and 700 degrees C maximum temperature of the cycle. So the key point is that this fluid should be capable of condensing at temperature below 60 degrees C. Here it is reported the delta efficiency, which is calculated from, again, numerical point of view between the CO2 blend and a reference CO2 recompressed cycle for two blends. Here on the left you have the first blend, and the graph here reports the efficiency, the delta efficiency. So when it's positive, it means that the CO2 blend outperforms the recompressed CO2 cycle as function of the pump inlet temperature and the turbine inlet temperature. As you can see, there is almost no variation of the delta as function of the turbine inlet temperature, but it's very, very relevant as function of the pump inlet temperature. And the difference can be as high as 1.5% more for the blend respect to the supercritical CO2 recompressed cycle for this type of blend. If we analyze another blend, this is even more relevant, the advantage of the CO2 blend with respect to the supercritical CO2. Actually, in this case, the efficiency gain can be as high as 3% when assuming 550 turbine temperature of the cycle. So we can claim that blend 2 is better than blend 1, and certainly they can outperform the conventional, quite conventional supercritical CO2 cycle, assuming a recompressed configuration. Last activity is about the validation, and here it is reported the test rig where the fluid will be evaluated in terms of heat transfer, stability, and dynamic of the system. And here is the picture. So far, what was performed, is the test tube was installed and the heat transfer coefficient was measured when comparing pure CO2 and CO2 blends through a smooth inner surface, and this is the case of the heat transfer coefficient, and when the improved inner thin tube by Kelvin was adopted, there is an enhanced heat transfer coefficient. Unfortunately, as of today, we don't have any further result from experimental point of view, and they will come in the upcoming years, I have to say, because it's not even in 2021, but it's 2022. These are the preliminary results. If you want to have more information about the project, we can follow us on the website, on LinkedIn and ResearchGate. And that's all from my side. Thank you very much for your attention. I'm happy to take any questions.
Thank you very much, Gianpaolo. So yes, if there are any questions, we have time, seeing as Gianpaolo is very swift and on time. Thank you. If you want to, if you need a bit more time to elaborate your question, you can always obviously put them in the chat. But I see, yes, Dieter, please.
Yeah, I have a question regarding the blends. You're talking about D1, D2. Can you say more about the blends? Maybe what proportion you mixed? I mean, how much CO2 content is left, for example?
Okay, that really depends on the blend, on the fluids you are considering. For example, D1, which is CCF6, the amount of CO2 is around 80%. Molar base, and 20% is the CCF6. D2 is TCl4, and in this case you have roughly 7% of TCl4 and 93% of CO2.
Okay, yeah, thank you. Just getting an idea what we're talking about.
Usually we consider it between the 5 and 20%, no more than that. Otherwise it's not blend, but it's a mixture, or so it's a totally different fluid.
Okay, thanks.
You're welcome. Thank you for the question.
Thank you. There may be time for one quick one still, but otherwise, please feel free to elaborate also in the chat. Huh?
Can I shortly jump in?
Yep.
Can you hear me?
Daniel,
yes, I have heard that this blend may be, let's say, too aggressive to the material, to the structural materials. Do you have some information about this?
So far, when we developed the, where is it? Here, the thermal stability test, which is performed by UniBS, we saw that you have to use Inconel or nickel alloy anyway at high temperature. And in this case, there is no relevant impact of the blend with the material. So I can say that if you go for stainless steel, yes, there can be, they are a little bit more aggressive, but since you're going to Inconel anyway at such high temperature, there is no major impact of the blend in terms of material selection and corrosion.
Okay, thank you.
Thank you.
Okay, well, Albany, you have to speak next. So if you have a question already, you can put it forward. But after that, then we'll keep the next ones for later.
Because if you go on a plant in Inconel or nickel-based alloy, don't you be afraid about the cost of plant? Because
there is a noise background. I couldn't hear the question. Sorry.
Please mute. Let's see, mute. There you go.
Is it okay? Oh, okay, yes. So yes, well, my remark was okay. As you know, the materials, it's a big question about the supercritical CO2 cycle. And if you go on a plant with a lot of nickel-based alloy, are you not afraid about the price of the plant? Because we know that it will be with a good reliability. Okay, we resist to some materials corrosion. Okay, but what about the cost? Because
yeah, certainly there is a point of concern about it. And when we wrote the proposal, it was around 3-4 years ago. There was really let's say all the research activity in CSP plant was going towards 700 degrees C. Okay, so that's why we aimed at that temperature. Nevertheless, throughout the recent years, there are many concerns that probably 700 is too high, so probably it's better to go down to 600. So what we are going to do is to understand and try to see from economic point of view whether it's worth going to such a high temperature. As you pointed out, using nickel-based alloy, it can be rather expensive. Nevertheless, in a CSP plant, the cost of the power block is quite limited anyway. So there are these 2 points which are one against each other. But we have to find this out within the next years of the project. Thank you for the question.
Okay, if there are any other further questions for Gianpaolo, please write them in the chat and we'll address them at the end. Albani, I'll give you the floor to present the sCO2-4NPP project.
Okay, again. Next, okay. So I will just switch my presentation. And you can just make me some noise if I'm too long, okay?
Sure.
It will be okay for me. So, okay, so yes, second project on this, okay. So yes, the project I will present now, it's maybe a little in marge of the other presentation because it's a project first proposed for a nuclear power plant. Okay. The idea was to continue the first works done in the former project sCO2-Hero and to continue this work and to continue to develop a system based on supercritical CO2 in order to make heat removal. So it could be compared to waste heat removal, but in our case, the idea is to heat removal when we could be in an accident situation for a nuclear power plant. So we want to remove the heat of the first loop, so the reactor of the plant. So the idea is, okay, we can maybe develop this type of system in order to increase the level of the safety of this nuclear plant. So the first objective is not maybe very common with the other project, but you will see that the system we are trying to develop is quite common that other project presented today. So our vision for this sCO2 system was to be able to produce some electricity with a decay height in order, for example, to be able to restart the plant from scratch if there is some problem with the current other system, to be very modular and compact, because in a nuclear plant or in like when you want to retrofit another plant or another industry, there is no place. So you have to be as compact as possible, to be with autonomous start, self-starting and self-sustaining, which is very important in some nuclear question about the safety, the reliability of this system, and to be retrofitted, to be able to retrofit this on the existing nuclear power plant, so pressure water, boiler water, and for the next design of power plant, so for the small modular reactor, for the generation 4, for new design of power water reactor. What we do first? First, we start to make a test campaign in a facility which was built during the former project sCO2-Hero. So thank you, Dieter, and all the sCO2-Hero team. So we perform some sCO2 test in a loop in Essen. What you see is a loop of nuclear power plant, and we put a very small supercritical heat removal loop in this loop, and the objective was to run tests and to provide some measurement in order to understand the starting of this type of loop because we want to be autonomous with a self-start, and to increase the complexity of the component involved in the loop, in the sCO2 system, in order to increase also our data. What we have as results was we improve a lot the knowledge of our supercritical heat removal behavior, because we understand how we can start, what could be the problem in interaction with another process. So it was very interesting, and it provides the required data for the loop modeling in some hydraulic, so thermohydraulic and nuclear codes. So the second step was to model this loop using 3 different thermohydraulic codes currently used in the nuclear topic. So the idea is that we have the same data, and we make the comparison between all the test data and the different model in the 3 codes. So Atlet, Qatar, and Modelica, which is not nuclear code, but which really often used in the nuclear operator and in industry. And so we made all this modelization. We performed some dynamic modelization. We want to understand all the transient as much as possible. We face off during the test, the first test campaign. After, as it was still a laboratory loop, we are working also on the development of the equipment in order to be able to provide the design of a 10 megawatt loop for heat removal. So we are currently develop a new turbo compressor, because we already have a design of compressor and a compressor in our loop, but now we are dealing we are working on a new design. So in this new type of compressor, we are working in order to test new type of bearings, so magnetic bearings, hydrostatic gas bearing, in order to see if it's possible to improve the flexibility, the efficiency, and also the reliability of this turbo compressor, which is very important because it has to be very reliable in a nuclear use. And this is a currently new design, so okay. And we also develop new type of heat exchanger. So for this heat exchanger, we are under a process of patenting, so I won't give too much detail. We be able to provide a very new design and a very still compact heat exchanger, because you can see some measure for our test loop. So we have an heat exchanger which is 43 centimeters by 16, so it's very small, and we are under a patent process for this new type of heat exchanger. Also, because it's a process which will be coupled with another process, in our case a nuclear plant, but we will have a coupling with an existing process, which is very important. We are working on this coupling of the 10 megawatt loop with a real power plant, and we want to simulate some accidental situation in order to understand and to see if our 10 megawatt loop is able to remove all the heat we want to remove, and to be able to self-start also, and to be able to run alone on autonomous way without any intervention of any human intervention, which is important because in the nuclear topic, we want to have very reliable cycle. So maybe the main idea is not to research the most efficiency as possible, but the most reliability and the most easy operation of the cycle. Okay, and so the results that we have preliminary assessment with the effectual effect of the system on the heat recovery, we saw that it's work. We are able to remove this heat from the reactor. So we are able to produce some electricity. So the first simulation, for example, with one of the codes, so Atlet, shows that with 4 modules of 10 megawatts, so 40 megawatts at the end. We be totally able to remove to decay the heat curve, which is very important. So we are able to take the control again of the reactor reaction. So it's very important. We have a very good control of the turbo machinery speed and a subcontract shutdown. And the system can run for more than 3 days, which is a common the common time needed for safety nuclear plant, because we think that if you are able to run for more than 3 days, to keep safe your nuclear plant during this 3 days even if you have in an accident situation, you will be able to protect all the safety and guarantee the security of all the people around. And we are able also to produce some power, so because the excess power is higher than 0, so we will be able to provide some power in order to restart the plant. We also work, because it's very important, and it was very important for all the participants of this project to work on the regulatory for this type of system. So there is two main way to work on this regulatory. First, we work on the regulatory for the nuclear plant, because we are in the nuclear sector, so it was very important. And we identified all the regulation and all the standard related to the nuclear safety system, and also all the regulation and standard dedicated to supercritical CO2 system. So it was very important, because for the first time, we say, okay, we be able to identify if there is some lack in the standardization and where we want to provide and what type of standardization we want to provide. So it's very important, because I think that if we are able, for example, to provide some standardization for supercritical CO2 system in a nuclear sector, it will be very easier to provide this type of standardization for all the other sectors, so all the other area of production. And also we identify the standard to be followed for the development of the equipment, which means that currently our industrial team who work on the development of the turbo compressor, the heat exchanger, follow very industrial standards. So they are not only on their test bench, their laboratory standards. No, they follow industrial standard in order to be able to say, okay, maybe we can go to qualification. We know how to deal with that, and we know what it means. What are the next steps in the project? Because the project is at the middle. We are at the middle of the project. So now we are working on the optimization of the 10 megawatt module design. So we will have a very ultra compact architecture, and we will be able to provide at the end of the project a final design of the main component. We will test some of the components like the turbo compressor and the heat exchanger on our first loop, but we will be able to test it and to provide the scale up after. We will also want to improve the efficiency, the operation of this system. We really want to have an autonomous system startup, and we want to improve the efficiency of the main component with a very important question of reliability also. It's very important for this system, more than maybe the efficiency. We just want to have a very reliable system. We don't know some problem with 2 days of running. Okay. We will still continue to simulate the CO2 system behavior. So we will test all the behavior of the system in a real nuclear power plant simulator, and we will optimize the coupling between the plant, the nuclear plant, and the system, and we will prepare development roadmaps like the technology roadmaps and the regulatory roadmap. What we think is that this system, even if we are not in the same scope of energies as the other project, could be very interesting because for the nuclear point of view, we have an innovative safety system and we will be able to use this system to produce some electricity in order to restart the plant. And after, we could imagine other applications like for industrial waste heat recovery and retrofit some other plant or other assets because we are very compact and we know that this module will run. And there is other important input for all the sCO2 cycle is that because we will test new bearings, so autonomous starters, and we will have the new heat exchanger design. So it's the end of my presentation, and you could see all the partners of the sCO2 for NPP project, which is still with some industrial, academics, and research institute.
Thank you. Great. So if there is any question for Albany, we can address that one or two now. Otherwise, as always, you can write them in the chat and we'll address them later on at the end. Okay, if there are no questions, then I will hand over the floor to Daniel to present Compass CO2.
Yes, hello. Okay, hello everybody. Let me start the presentation. Oh, wait, I have to share first. Okay. Can you see my screen and the sharing?
Yep, we see it.
Okay. All right, great. So my name is Daniel Benitez. I work for the German Aerospace Center, DLR, and I will present you a general presentation of this project, Compass CO2. In the presentation, I will give you some of the boundary conditions in the project, then give a short description, the technical aspects, send you the current results, and then discuss a little bit about how can we cooperate with other EU projects in this scope of supercritical CO2. So the project Compass CO2, its full name is Component Material Performance for Advanced Solar Supercritical CO2 Power Plants. It's a Horizon 2020 research and innovation action, which is supported by the SPIRE Association. The project started on November 2020, has a duration of 4 years. There are 12 partners in the consortium coming from 7 countries. So the main goal of this project is to integrate two innovative systems in order to tackle the challenges presented at the beginning from the EU. We have this innovative CSP plant with particles. There will be a solar tower plant, and of course the supercritical CO2 Brighton power cycles. We have noticed that the integration of these two is very challenging because the materials that are needed will under harsh conditions regarding high temperatures, high pressure, erosion, corrosion mainly. And this project is a material research project. So as for the objectives, we will work on the development of, let's say, new particles for CSP plants. Then also work on the structural heat exchanger tubes, which are in contact with the particles and the supercritical CO2. To demonstrate the lifetime of the materials by testing them and modeling the degradation. Then to design, construct, and operate a section of a particle, a CO2 heat exchanger, which we'll use to validate the models. And finally, to evaluate the economic benefits of such a plant, and of course, compare it with the state-of-the-art CSP plants. Then I will jump quickly into the results. So an overview of the main results we have, for instance, regarding the Brighton cycle, our first deliverable, shows our literature research, the different configurations that we found. As many of you here know, there are many options to create a supercritical CO2 cycle. So we look at the difference. We notice that there is no clear, let's say, preferred cycle. So we analyzed 10 of them, from simple cycles to recompression cycles to partial cooled cycles. and valid 6 parameters shown in the table below. So turbine inlet temperature, compressor pressure, and other parameters in order to identify which one suits better for this application of CSP plant. After the optimization, we focus on identifying the cycles that for a very high temperature offer especially the highest efficiency. This is because for this call from the framework of the SPIRE Association, they were looking for materials that withstand very tough conditions, and we identified that, okay, as some colleague before mentioned, there are state-of-the-art materials like Inconel alloys that can withstand up to 650 degrees. But we noticed that there are interesting, very high efficiency to be reached if we can expand this temperature to 700 degrees. So therefore, that is the scope of our project, the 700 degrees temperature at the turbine. Selected for that the highest efficiency. Nevertheless, the levelized cost of electricity is not the lowest. We're looking now at the configuration 9, what we selected. But then the focus of our project is to search for materials that can allow this cycle to be competitive. So then after the optimization, we set a set of parameters that were used to design the solar plant and the heat exchanger. Okay, as for the solar power plant, we have done the simulations for a power plant in South Africa with 112.8 megawatts net output, and with a maximal particle out temperature of 1000 degrees C in the receiver. So this is much higher than the of our molten salt, which is our benchmark, which we compare, and of course want to improve. For this system, the type of receiver is the so-called Centrac receiver that DLR has been developing since many years, has a maximum power, let's say around 100 megawatts. So therefore, we need 6 towers. It's a so-called multi-tower system with a large storage of around 12 hours of full load discharge. Then we have done the LCOE optimization of the CSP plant, mainly the heliostat field for the location and for the tower size and for the temperatures obtained and so on. Then we move on designing also the heat exchanger, which has been selected as a moving bed heat exchanger. The partner John Cockerill has been working on it. It has tubes containing the supercritical CO2 in the inside and particles, ceramic particles flowing by gravity around the tubes. Okay, so if we look closely at the parameters, what we're saying, the particles that flow into the heat exchangers will come around 900 degrees C. And another important level is that the temperature of the supercritical CO2 coming into the turbine or out of the heat exchangers will be 700 degrees. And the pressure, that we have a maximum pressure in the system of 265.3 bar, which is also very high, very demanding for materials. So first we work on the selection of state-of-the-art alloys. We can find Inconel 740 or Heinz 282, for instance, that can withstand them. Based on that, let's say a preliminary design has been done of a heat exchanger for a commercial application. We have noticed that it would be, of course, a very large component with about more than 60 tons of Inconel 740 with 30.8 millimeters thickness tubes. This, of course, has a high impact on the cost. We are also, of course, thinking on combining with lower cost materials for lower temperatures at the bottom of the heat exchanger. But at least for the, let's say, top design, we have the top of cost design. We will have this 740 tubes. This is the state-of-the-art selection. So then we have analyzed, or we have noticed that there are many challenges to this application in specific, as I mentioned. We have the particles moving outside and the supercritical CO2 from the inner wall. Therefore, we have high mechanical loads due to pressure and temperature, there is a corrosion due to CO2 itself, and we have for oxidation and erosion on the outside due to the particles. Therefore, there is a, let's say, this flow that we will follow in order to evaluate the materials and to develop new materials, starting with the selection of promising materials, or which new materials are being developed that could fulfill our goals. And also we're working, or we'll work on coating systems to the tubes. Then the test will be done to verify under this harsh condition regarding oxidation, corrosion, wear, and mechanical properties. Then based on this degradation mechanism, we can work on models. That's a specific partner will be working on models, and with that we can verify if modifications on the alloys can then be of improvement. And once the material has been selected, then we will demonstrate it on a pilot plant, a heat exchanger pilot plant. I will not go very much into detail of this, but just to give you an idea, we have been looking at the materials that can work on several temperature ranges. And we also noticed that depending on the materials, of course, we will have a different wall thickness. And this is very important for the heat transfer coefficient in the heat exchanger. So this is an iterative process. If we select a material that requires a too thick wall thickness, then the heat transfer is not so good. Therefore, the temperature rise on the outside. And then we will need more tubes, the cost increase. So this is an iterative optimization process we are following. We have also noticed about the corrosion and mechanical degradation is very important depending on the environment that we have. In this case, the supercritical CO2 is very challenging for the materials. And also, if we look at the impurities, this is also very important. In the power plants, normally we don't have so-called research grade 100% or near to 100% CO2, but we have some water or oxygen impurities. This affects the lifetime of the material. Also, the corrosion due to the thermic cycles is very important for CSP plants, because CSP plants do not work like nuclear plants 24/7, but they have some variations depending on the storage size. And depending on what I've seen from the literature is that the cycles have, depending on the material, can have a very strong impact, reducing the lifetime. So we will also work, as I show in the next slide, on cycling thermic cycles to evaluate the lifetime. And another topic that is quite, let's say, important, is very important, and it's quite new, is the erosion of the tubes from the outside due to the particles movement. This has not been, based on literature research, has not been well, let's say, investigated, maybe because this application is quite new. And but it's indeed very, very important, because we will also face material loss from the outside. So for that, looking at the test, we have several partners designing tests to evaluate erosion at high temperature, for instance, also oxidation at high temperature with atmospheric CO2, also CRIP at a high temperature with air, thermocyclic testing with CO2, as mentioned. It will be very interesting tests to be done, as well as CRIP tests at high temperature and atmospheric CO2. Furthermore, as I mentioned, we will work on the development of materials. We have two partners are working on two key new materials called this chromium nickel alloy, aluminum alloys, or chromium silicide alloys from Descheman from University of Birmingham. They already have a couple of PhD students working specifically on this topic, because, as I will mention later on, not only for this application, but for other applications, such, let's say, high-tech materials can allow new technologies to be real, to be applied. And also coating is an important topic. Coating of existing substrates will be analyzed. Okay, and the second material that we're evaluating are the particles. Currently, ceramic particles, so-called propants, which are normally used for fracking industry. They have been used for CSP applications until now, let's say on small demonstration volume or capacities. But we have noticed that they have also some disadvantages, especially regarding aging of them. And of course, we would like to look for particles that are better suited, that are, let's say, specifically made for CSP. So we're looking at the shape, the color, their durability. The partner Saint-Gobain is working on the production of new types of particles using the methods of granulation and electrofusion. They're also looking at to maximize the density and the heat capacity in order to reduce the volume. For instance, the volume of particles in the storage system of CSP is very large. So if we reduce that, this will be very helpful. They're looking at using raw materials, for instance, from the steel industry to optimize cost, and also to see what is the impact on the cost and on the performance if we can select a larger range of size distribution. This is also very interesting to be analyzed. Particles will be produced in small and large scale batches to be tested. And then we will evaluate and characterize them optically and chemically and compare it to state-of-the-art particles. And the cost will be estimated, and of course their durability. We have also set a set of key performance indicators to be fulfilled, keeping the costs as high as the current state-of-the-art particles, the propants. So there is a set of tests to be done that have been designed. We're working on the construction of test rigs to for instance, demonstrate the resistance under high temperature, because the particles have also some impact. They're moving through pipes and through the transport system and from the receiver, so it's important that they are durable. So we have impact tests, and rotating tests, and other kind of impact tests were going on. Another interesting topic is the coating also of the particles themselves. We can look for, let's say, particles that are cost effective but are not really dark, because let's say this dark color is important for CSP in order to have a high absorbance, and we also want to have a low emittance under working temperatures. So this coating is being analyzed, and of course we need to evaluate the effect of aging, their durability. And finally, another topic that is important is the modeling, let's say design of materials through computer systems. We have a partner from Finland, VTT, working on the evaluation of a microstructure, how these materials behave, also the coating on the computer models. Also important about the manufacturing process or welding will be interesting. What about the stress? All this can be done with computer programs, and they're also working on machine learning optimization for searching for the, let's say, ideal composition for the application. Okay, now just to inform you, we have several dissemination tools, communication tools. We have our website, compassco2.eu. We have the Twitter channel and the LinkedIn. You will get the links from the presentation. We prepared a newsletter, and there's on our website you can download the public deliverables. The first are focused on the boundary conditions of the CO2 Brighton cycle and the solar plant. And we have other confidential reports, but of course you can contact us and see if we can share more details with you that we have published until now. And to close, as I mentioned, and I think was the scope of this presentation, is to see how we can cooperate, how we can bring forward technology of supercritical CO2 power cycles. Therefore, I'm sorry, yes?
Non, non, du tout. Attends, je coupe le son, j'ai une conférence.
It's okay, Daniel.
Yeah, Daniel, sorry, there was somebody with the mic open, but we muted. I don't know if you're still there. Just to conclude.
Hello.
Okay, great.
Okay, I didn't. Sorry, I didn't know my mic was muted, but this is just 30 seconds left. Yes, I said we can work with other projects on the optimization of the Brighton cycles. As we have seen that there is a lot of potential. We can think on other applications for the particles, also other applications for the structural materials that have been developed, especially if you have some harsh conditions. We can cooperate regarding testing and modeling of material degradation. We can think of some round-robin testing, for instance, of some specific conditions. And finally, we can work on joint publications or some dissemination events for those topics in which we can have some synergies and some, let's say, some expansion from other projects. Okay, so that's for my presentation. Here you have my contact data, and also from my colleague Abdel Ghani, he's the communication and dissemination manager. And there is a list of partners. If you get the presentation, I think you even are able to click on the links and visit the websites. Yeah, so thanks a lot. And please let me know if you have any questions.
Thank you, Daniel. Yes, just to say that all presentations will be made available on the sCO2-flex website once the event is over. If there are any questions for Daniel, otherwise we have foreseen a 10-minute break. Albania, I see you raise your hand.
I think Paolo was first.
Okay.
You can go, Albany, no problem.
No, you can, Paolo.
Okay, yeah. A quick question. Paolo from Politecnico di Milano, from sCO2-flex project. My question is about the choice of the storage capacity. You mentioned 12 hours, I remember. This is for dispatch reasons, or it's a kind of size that will minimize the LCOE? And did you find really the advantage of such a sizing of the storage to decrease the LCOE with respect to a plant with a minimum storage or without storage? Thank you.
Yes, thank you for your question. Indeed, this factor, this parameter, let's say, was fixed from the beginning. We were looking for base load power plant. This is an application. I will say it's for simplicity. Maybe you're thinking on hybrid power plants. There is, let's say, a new trend of working on hybridization with PV, in which PV works during the day and CSP storing the energy with a smaller storage only for the night. But this will, let's say, make it more complex. We say we will work on baseload power plants. Therefore, we selected quite a large storage. We did not optimize the storage size in this case. This was just said. Probably, as you mentioned, would be another optimum, economical optimum, if we maybe reduce the size. But in that case, we will also have to reduce it to the, let's say, benchmark. We have said we're benchmarking, comparing with also baseload molten salt power plant in order to evaluate the economic aspect.
Yeah. Okay, so it is for dispatching reasons. I intended that there were a minimum of the LCOE due to that size of the storage. Okay, thank you.
You're welcome.
Any last quick question? Otherwise, I think we can have a short break here. We were running 5 minutes behind the original schedule, so Albania, I don't know if you agree. Maybe we can either take 5 minutes break and stick to the schedule, or we make it 10 minutes and just give a little bit more time to breathe. Up to you.
It's okay. I just have a little question for Daniel.
Oh, sorry.
Maybe I missed the information. I'm sorry if it's the case. Do you intend in the project to see what could be the other gain possible with sCO2 for solar? I mean that one of my questions is that what could be the gains, the decrease of water use, for example, with a supercritical CO2 cycle instead of the current cycle for solar plant. And do you think that it's possible to reduce a lot the footprint in order to put, for example, all the turbo machinery, the production cycle in the tower, in the solar tower, and not at the side of the plant.
Okay. For your first question, because the second part I didn't understand very well, but regarding the water usage, if we are planning to optimize it, in this case, no. We have seen that there are other projects working on this. So we have focused mainly, because this is a material development or material research project, we're focused, let's say 90% on the heat exchanger, means the tubes and the particles that are in contact there. We're not looking at the orbital cycle. This cycle selection was, let's say, more or less quickly done. We will not optimize it further. So we're not looking at this impact of the Brighton cycle. That from we're aware that it's important. We're also very aware that the ambient temperature is, let's say, is a key factor on CSP plants. This is why Project Scarabeus is very interesting for us to be able to increase the ambient temperature. And that was a big part of my question before, because we're looking at the impact on materials of the additive of these blends, but we are not. I mean, just to say, we are leaving this question to other projects, how to optimize the cycle for lower water consumption and higher ambient temperature. But it's not the focus of our project. We will do a short, let's say, business case evaluation and environmental impact analysis at the end, but this is not on the focus of optimization. And the second part of your question regarding the tower system, I did not really understand it. Albania, you are muted in case you are talking.
Okay, no, I just say that it was one of my favorite topics with supercritical CO2. It was the footprint. So at the beginning of our reflection about the SCO2 cycle inside the DEF and with other people, we had the dream that with a supercritical CO2 cycle, we will be so compact, so little, that we can put all the turbo machinery inside or in front of the solar tower, and not just another part of the cycle, but it's okay.
Okay. Now I understand your question. Yeah, I don't know about this. I don't know. We haven't thought about these details, where it will be located and how we can save some cost with that. I mean, this tower, in this case, we will have, I think if I remember right, 130 meter towers, so they're quite large. Probably no, I'm sorry, no. In our specific case, it will not be possible to integrate, because we're thinking on 6 towers. It's a multi-tower system, so it's not just one tower. The power block will be in the center, and the particles will be transported with particle transport system, which is being developed in a separate project. So the power block and the storage is, let's say, on the center, where the storage is integrated on each tower, and then the power block in the center of the 6 towers. Yeah. I hope this answers your question. You're muted in case you're.
Thank you, Daniel. Yes.
Okay.
All right. Thank you.
Okay. Thank you. So maybe we might save any further questions for Daniel and all the other projects that are presented so far for the end. Now we have foreseen a 10-minute break. So I would suggest to, grab a glass of water or a coffee and come back for 4 o'clock. If you agree, Albany, obviously, and everybody else.
Yes, I will need some coffee. It's okay for me.
Okay.
Yep.
So
you.
see you again in 10 minutes for the next presentation, which is iTherm.
I think Dieter also needs some coffee.
Great. Okay, so see you at 4. Thanks.
O stanno from break.
Sì.
Okay. So it's 4 o'clock, and I see Savas. Is that how you pronounce your name? Thank
I
you.
will stop the publication, the publicity for the conference. It's okay.
we can talk about it after. Yep.
Yes, we will talk about, but
Yeah.
Dieter will talk about.
Good. Okay. Without further ado, Savas, yes, please share the presentation for iTherm. me know if are you okay with sharing the presentation yourself, or yeah, okay, yeah, I think it's coming. Great. Yeah.
Okay, now let's see. Is that okay?
Yeah, perfect.
Good. Can you still see it? Yeah.
Yeah.
Good. Excellent. Let me see whether I can.
You're on slide 3, just so you know.
I'm on slide 3. Okay.
Yeah, slide 3.
Oh, I think I'm showing. Okay, now slide 1.
Yeah, slide 1.
Great, excellent. Good afternoon, everybody, and thanks very much for the opportunity to present at the meeting this afternoon. My name is Savastasu. I'm from Brunel University, London, and I'll be presenting the ITERN project with my colleague Matteo Marchioni. Now, first of all, a few words about the Brunel University London. Brunel is a medium-sized university just at the outskirts of London, very close to Heathrow Airport. We have approximately 15,000 students and about 700 academic staff, and a turnover of about 270 million euro per year. Now, my research team is involved in a number of national programs, but also EU-funded projects, the ITERN project that we'll be talking about in the next few minutes, and then that we are coordinating. Then we are involved in a more recent project called A-STEP, which is the application of solar thermal energy to industrial processes, and of course the new project COOL-HEAT that Google will be presenting, I think, later on. Now, the aim of the ITERN project is to investigate, design, build, and demonstrate innovative plug-and-play waste heat recovery solutions to facilitate optimum utilization of energy in selected industrial applications with high replicability and energy recovery potential. And we are looking at temperatures in the range 70 to 1,000 degrees C. So what we need to note here really is that the ITERN project is not entirely on CO2 technologies. CO2 is one of 4 technologies that we are looking under the ITERN project. Now, the objective of ITERN is to develop heat recovery and heat to power conversion technologies in a package or easily customizable plug-and-play forms that can readily be applied in industry. Develop an intelligent system for monitoring and online integration and control of the operation of these technologies to maximize heat recovery and conversion. Implement, monitor, and evaluate the performance of the technologies and the environmental impact, as well as energy consumption and CO2 emissions, and of course disseminate the outputs. ITERN involves 13 partners, 3 large industry partners, 7 SMEs, and 3 RTDs from across the European Union, including the UK, of course, now. As I mentioned earlier, we are working in the temperature range with different technologies from low temperatures, 70 degrees to 1,000 degrees C for radiant heat recovery from very, very hot industrial processes. We are looking at 4 different groups of technologies. Heat pipe technologies that can recover heat from radiant sources, from very high temperatures, heat pipe technologies to be used as condensing economizers for combustion processes to recover heat from combustion processes, and then a low temperature heat to power conversion system the trilateral flash cycle for low temperature applications below 100 degrees centigrade, and then the supercritical CO2 cycle for heat recovery and power conversion over a temperature range above 300 centigrade. Now, the trilateral flash cycle system is a three-leg sort of technology where you expand from wet conditions. Is like an ORC system, but we expand from wet conditions to increase the power output potential of the unit, working at low temperatures. I'm not going to spend time on this technology now because, of course, the objective of this afternoon is to talk about sCO2 technologies. But just showed you here really the developed technology and the monitoring system and the application of this technology to recover waste heat and convert to power from a steel plant in the UK. It's a Tata steel plant. Now moving on to the supercritical CO2 technology. The objective was to develop and demonstrate the 50 kilowatt system and using temperatures. I mean, the initial is to have temperatures up to 800 degrees C, but the system really was designed for temperatures up to 500 degrees C. The demonstration site is at Brunel University because at that time it was one of 4 technologies that we were developing, and it was very difficult really to find an industrial site that would accept such a high-risk technology with such a low power output. So we had to build test facilities at Brunel University to enable us to test the sCO2 system. It's a simple, we are using a simple regenerative cycle. We've done quite a lot of analysis and simulation looking at different cycle configurations, but we identified that the simple regenerative cycle is the best cycle in terms of a compromise between efficiency and capital costs for the unit. And because we are recovering waste heat, really efficiency is not very, very important. So we went for a simple cycle, the regenerative cycle, and here it shows you in 1D model, the model of the cycle. Operating parameters, pressures in the range between 75 and on the high side 128 bar, but it can go up to 140. That's the limitation of some of the components we have on the cycle. Temperatures, operating temperatures on the high side at 40 degrees, and a CO2 mass flow rate of about 2.2 kilograms per second. This here shows you some of the facilities we had to build for the project that really they were not costed in the project, so we had to find significantly additional money to really enable us to build the facilities. So we will establish an 800 kilowatt thermal heat source. The process air heater, we're using natural gas to generate the heat. And then here you can see, I hope you can see my pointer. We have the air heater here. We have in a container the sCO2 or power block, and then we have heat rejection at the top of the platform there through water. I shows you the power block in the container. That is a 20-foot container. This is The recuperator, we are using a Heidrick recuperator for this for the project, using electrically powered diverting valves. I mean, this is a power the CGT unit manufactured by partners in France. The rotors are very, very small because of the small power of the system. With regards to the heat exchanger, the heater we're using developed a microtube design, sort of a large number of tubes arranged in different sort of bundles, as you can see here. We have tube bundles with a number of microtubes, 1 millimeter diameter tubes made of Inconel, so using Inconel for this heat exchanger. And this heat exchanger is placed in the duct of the process air heater, and then the printed circuit heat exchanger, which has been sort of developed and well established by Heidrick, using 3D modeling of the heat exchangers, particularly to optimize the design of the microtube heat exchanger, but also different configurations of plates for the printed circuit heat exchanger. So we've done quite a lot of modeling in this area, both 3D CFD and 1D CFD to use in the steady state and the dynamic simulation of the system. And here this slide shows you some of the work that we've done on the optimization of the printed circuit heat exchanger, particularly headers, and so on, to reduce pressure drop and ensure sort of uniform distribution, and also establish heat transfer coefficients for the unit. Then we developed monitoring and control and communication systems, because we were running 4 demonstration sites in different locations that really wanted to collect from all the demonstration sites data centrally, and then make the data available to all the partners. So we have Matteo that is going to talk next, really develop these monitoring and communication systems for all the technologies, but in particular the sCO2 system. So Matteo, I'll pass on to you now.
Yeah. Thanks, Professor.
So you want to talk about this slide and then move on?
Yeah. Good afternoon to everyone. This one basically here we used a particular node standard, which has let's say the peculiarity of this kind of standard is that allows to develop a control system with decentralized applications, which basically increase the reliability of the control system, and as well it poses the basis also for decentralized power generation control. Basically, the centralized platform also communicates with an online platform that allows to take also high-level decisions, as for instance the operation of the unit at part load, following not only the data monitored by the sensor, but also, for instance, real-time price data about electricity or heat. Professor, I don't know if you can. Yes. So also we developed some modeling tools that allows not only to model the system and standalone components at steady state, but also with transient simulations, when we can get valuable insight on behavior of components. And Prof, if you can advance, yeah. And also this, of course, allows to simulate the system as a whole unit. And what we really understood with this analysis is, even if we are dealing with a small system, that means a total charge of CO2 around 60-70 kilograms. Basically, the startup procedure will be tough and cannot rely only on heat additions, but basically requires the first buildup of pressure into the system. Also, what we investigated is, let's say, the control variables that are available. Being a small scale, we really have not so much choices. So what we compared is turbo machinery speed and inventory control. Our objective, of course, is an heat load following approach, meaning to try to optimize the system performance independently on the heat loads by the primary heater. To do so, what we try to do is to control the turbine inlet temperature. Here you can see some let's say, preliminary numerical analysis where we show that really inventory can provide the regulation without impacting so much the system performance. And also what we investigated is the inventory control by considering finite capacity tanks. And here the problem is really the tank sizing, because it impacts not only the performance of the controller, but also let's say, the durability of the control action, because once you, for instance, fill the system with additional CO2, for the next regulation, you will have basically a pressure drop in the tanks, and so you will have to accurately manage the inventory tanks. Yes, future developments, we are basically in the commissioning stage of the turbo machinery, and once completed, we will be able, of course, to test and validate the models, and also use the facility to investigate more advanced heat exchanger technologies, testing the control strategies that we analyze numerically, and also different turbo machinery arrangements that could potentially bring many advantages in terms of control and performance. So yeah, that's all from my side. Progress.
Any questions? No.
Bang on time.
Okay.
If you have any questions, please raise your hand, or otherwise write it in the chat. If there's nothing, nobody raised their hand, then I think we can already proceed to the final presentation.
Okay. Stop sharing.
Okay. Thank you, Savas. I don't think there is any questions at the moment. Yeah. So yes, Ugo, I hope you're still there.
Yes, I'm here.
Great. And yes, final presentation of sCO2 to all heat.
Yes, thanks a lot, Gustavo, and good afternoon, everyone. Thanks for inviting me, and also giving me the opportunity to present this newly started project, the Cool Heat, which stands for Supercritical CO2 Power Cycles Demonstration in Operational Environment Locally Valorizing Industrial Waste Heat. So the project started officially on the 1st of June, and just on Monday and Tuesday, last Monday and Tuesday, we had our kickoff meeting. So I'm going to give a general presentation. We still don't have results, as you can imagine, but happy to take any question at the end and then try to answer or address them internally. So in a nutshell, the Cool Heat project aims to unlock the potential of industrial waste heat and transform it into power via supercritical CO2 cycles. And so it will be developed a 2 megawatt power block able to valorize the unused waste heat. There will be a demonstration done in a cement plant in Prakovice. And also 6 replication sites for 6 different industry in the resource among the resource and energy intensive industries. So at EU level, this is the first of its kind EU megawatt scale waste heat to power SCO2 plant. We have a consortium of 21 partners from 10 European countries. The budget is almost 19 million euro with a contribution, EU contribution of 14 million. The main goal is to design a novel integrated waste heat to power plant layout to untap industrial waste heat valorization at a temperature which is higher than 400 degrees Celsius in an efficient and cost-effective way, and also the development of an innovative, economically viable and DC replicable SCO2 power block via an integrated, easy-to-install skid. And of course, the goal is finally to increase the energy efficiency for the resources and energy intensive industries while enabling grid flexibility, targeting an LCOE of about 0.05, 0.06 euro per kilowatt hour in the scale of 5 to 20 megawatt. And therefore, there to enable then the end users, so also this heavy industry, to switch their role from consumers to prosumers. As I said, the project started on the 1st of June and it will last till the 31st of May 2025. After the first year, we are planning already to have the first plant layout definition, optimizing also the cycle according to the end user's needs and requirements. By 2023, we are aiming to have the complete SCO2 power block design. And by 2024, then we start with the installation and commissioning of the power block at site, and the last year will be dedicated to demonstration of the operation of the power cycle, the power block. So the specific objectives of the project, there are some technical, some replication, and then some objectives related to the impacts. In terms of technical objectives, we have the development and demonstration of a 2 megawatt highly flexible SCO2 waste heat to power block with the heat temperature above 400 degrees Celsius and an efficiency which should be above 23%. The development, this would include also developments of power cycle components such as turbo machineries and novel heat exchangers, development of new control systems that would enable the flexibility enhancements related especially to the part load or lower waste heat temperature, and also for power grid interoperability. We are aiming also to replicate this concept in 6 different applications. So in the aluminium, steel, glass, concentrated solar power, waste incinerator, and combined cycle gas turbines. Therefore, we have all the end users on board on this project. And of course, to also, because this is the first of a kind power cycle and power block demonstrated at EU level, we are also aiming at create a pan-European SCO2 working group in which we can discuss the development of SCO2 related topics. And in terms of objectives related to the impacts, then demonstrate economic and replication feasibility, environmental impact, and social acceptance. Here in the picture, you can see first diagram or very draft diagram of how the power cycle will be integrated in the cement plant. We have basically 3 loops. We are going to recover the waste heat the waste heat from the cement plant, and so this is the first loop, as I said also before, at 400 degrees. And then we are going to manufacture and then install a skid with on it a turbo machinery with a compressor and a turbine on the same shaft, ideally, and a second power turbine connected to the generator. And of course, we have also recuperator and then a number of other 2 more heat exchangers that would exchange the heat with waste heat from the cement plant and also from the cooling tower still in CEMEX. This is a very first draft configuration, which still needs to be studied. So we will most probably there will be changes according to the studies that will be carried out. Yeah. So the demo site will be hosted by CEMEX, big cement company in Prakovice in Czech Republic. And where the waste heat potentials that we have identified is of about 16 megawatt thermal. And it is, as you see, this is the basically a picture of the plant. And initially, we have identified 3 potential points in which we could recover the waste heat. And finally, we are discussing where to install the skid. And this will be based on a number of considerations like the layout and the waste heat and also the temperature. So in terms of replication sites, so we have 6 replication sites. We have first one is the glass industry. So the sCO2 in the plant is located in Ankara, where we have a waste heat of about 20-25 megawatt thermal and the temperature which is about between 450 and 580 degrees Celsius. The second replication site will be hosted by the Mytilineos, the aluminium industry in Viotia in Greece, with a waste heat of 1142 megawatt thermal and a temperature 443 degrees Celsius. Then we have the waste incinerator plant in Beringen in Belgium, which will be studied by Engie Laborelec. Which has a steam capacity of about 102.5 ton per hour with a temperature about 400 degrees. The fourth replication plant is the steel production plant of Celsa in Barcelona. And then we have the fifth replication plant is the power generation for the combined cycle gas turbine plant hosted by EDF, managed by EDF in Montereux in France. And finally, we will study also the replication of cool heat concept in the power generation concentrated solar power plant in Cordoba. The methodology of the project. So we have 4 phases. The first phase will be the assessment phase. So we will study the cool heat layout. We will optimize the layout and the cycle based, as I said, on the needs and requirements of the Prakovice pilot plant, but also taking into consideration the replicability of the same concept in other replication sites, so that because the aim of the project is to bring the technology at TRL 7, then at the end of the project, the technology would be ready to for the next phase of commercialization. Then the second phase would be the enabling technologies development and pre-demonstration phase, in which there will be the components design and realization of supercritical CO2 turbo machinery, the balance of plant, the heat exchangers, and the control development. The third phase is the demonstration phase with the commissioning and the installation in the Prakovice plant. And then across the entire duration of the project, then we have the impact assessment, replication, promotion and policy in which it will be studied the business cases, the replication of the concept, and also, as I said, the creation of the sCO2 EU working group. So this is the consortium. As you can see, we have the main manufacturers and of turbo machinery involved, and especially the one on working on supercritical CO2 worldwide. So we have a number of end users to make sure that the concept is replicable, and also all the key academia partners that, as you could see also from the other presentation, they are already involved in many other projects. And so we believe that this strong consortium can really pave the way for future deployment of the sCO2 concept, the technology. Well, so in terms of impacts, these are the expected impacts that we have studied in proposal phase, and that will be obviously have to be validated through the development of the projects. So we are also aiming to enable the resource and energy intensive industry to become flexibility actors in the grids, and therefore to switch their role from consumers to prosumers. This means that this is thanks also to the sCO2 power block characteristics, so which has a higher flexibility compared, for example, to other waste heat to power solutions, such as the steam cycle or the organic Rankine cycles. They have a higher efficiency, especially when we go for higher temperature and above 400 degrees Celsius. It is also, they are modular and compact, which also would easy the installation and the integration in the plant layout, and it would be also easy to scale up the technology for higher power levels. As you can see here, we have estimated what is the efficiency of the sCO2 power block that will be developed in the project, both for resource and energy intensive industry, for power output of 2 and 5 megawatt, and for power generation with the power output of 2, 10, and 15 megawatt. In terms of environmental impacts, it has been estimated at EU level that theoretically the waste heat recovery is about 918 terawatt hours in the EU 28 member states, which means that we have this technology, sCO2 technology, if deployed in all these energy intensive industries, could have a very high impact in terms of reduction of greenhouse gas emission, but also in terms of primary energy savings. So increase the primary energy savings for this industry, that heavy industry that would be able to produce internally the electricity. And so for the CEMEX plant, we have estimated that the primary energy saving deploying the 2 megawatt power block would be more than 40,000 megawatt hour per year, and with a reduction of greenhouse gas emission of 6,496 ton of CO2 per year. We would have a reduction of up to 100% of water consumption if, for example, we would install a steam cycle to generate the same power. In this case, the sCO2 technology doesn't need water, or reduced consumption, and also reduced up to 30 and 40% of components raw material, thanks to the compact size of the technology. In terms of economic impact, we have estimated an LCOE of about 4 or 5. It depends also on the power output, 4 or 5 euro cent per kilowatt hour, which means that the Prakovice plant would avoid, the cost of electricity avoided would be of about 800 euro, with a payback period that is between 4.3 and 7.8 years. The rate of return of the CO2 system is about 18%. And in terms of global market potential, here we have estimated for the entire waste heat recovery, let's say, industry by 2030, then the market potential could be about 60 billion euro, and by 2040 we estimate it to be about 200 billion euro. And of course, one of the most expected impacts is to change the role of these heavy industries from consumers to prosumers. You can see on the left-hand side what is the estimated capex for the power block, both for the resource and energy intensive industry, in which the equivalent operating hours are about 8,000 hours per year, while for the power generation, the equivalent operating hours we estimated to be 5,000 hours per year. And we made, obviously, there is a difference between 2 megawatt, 10 megawatt, and 15 megawatt power plant. Yeah, so this is the project structure. We have two different levels: strategic level and more operational level. Now the project coordinator is ETN, and together with the RINA Consulting. We have a general assembly and the steering committee. The steering committee is the one in which we will take more technical decision, more operative level. And then we have a demo committee which will give more instructions and guidance on the demonstration activities. And of course, one key committee is also the dissemination and exploitation committees, to make sure that then all the results are properly disseminated. So here you just see an overview of the different work packages that we have. So we have well, the first work packages is focusing on the scenario analysis and requirements definition, while the work package 2 and 3 is more the development of the turbo expander units and the turbine. And then we have work package 4 on the heat exchangers and work package 5 on the dynamic simulation and control. Then we have a work package dedicated to the demonstration campaign in Prakovice, and one dedicated to the replication and impact. And then we have one work package for management and one work package for dissemination, communication, and exploitation activities. I think this is all on my side. Thank you for your attention, and if there is any questions, I would be happy to take it. Albany.
Hi, Hugo. Just a very quick question. If I remember, it's a 4-year project, so you will finish the project in 2025. Do you think that the CO2 technology will be ready for the market by the end of the project or just after?
Yeah, I think yes, there is an opportunity. I believe that in 4 years at least, yeah, this could be a technology that could be then deployed on the market. Yes, at least that this is our aim and this is our objective. So.
Thank you. I think that's a very good argument for this project is all the replication case, because you will deal with a lot of different waste heat recovery needs. So I think it will be a very interesting project, and I'm waiting for the results.
Yeah, no, indeed, the fact that we have so many end users and so many different business cases involved in that will be carried out in the project, and then end users that are directly involved in the steering committee of the project and will steer also the direction of the project. This will make also sure that then the technology is developed on users' needs. And that's also the reason why I believe at the end of the project, at the end of May 2025, this will be, well, one technology will be directly installed in Prakovice at Cemex plant, so they can start producing electricity by their own. And the other end users may evaluate the possibility to install the same technology also for their plant.
Thank you, Hugo. There is several questions. One question from Eric and one question from Paolo.
Paolo, would you like to go first?
Okay. Ciao, Ugo.
Ciao.
Thank you for the presentations. I have a question here related to the cost, the capex. Today, during the final discussion on the supercritical CO2-flex program, we saw that for a 25 megawatt of power plant, the estimated cost is around 4,000 euro per kilowatt. Now, if we are talking with the COLIT program about, we are speaking about the industrial application. In your opinion, there is a target price that allow to this technology to drive the energy transition with helped by the supercritical CO2 cycle? How much could be the cost for kilowatt? The range, obviously. Do you have an analysis, a guess? Because looking at what I found in the previous months about this argument, there are a lot of debate here, because at the end of the story is the key point here is to balance the efficiency that we want, that should be enough for sure to be below the standard technology, but it has to be balanced respect the capex. Otherwise, you can't address the market. So I don't know if you have an idea of this target cost in terms of capex.
In my opinion, the costs now for the technology depends also on the materials that the manufacturers will use. And if we are addressing like some processes in which the waste heat temperature is maximum, let's say 400 degrees Celsius, then the type of material that can be used may also be cheaper than if we are addressing instead of waste heat temperature, which is above 400 and up to 1000 degrees Celsius, like for example, the steel industry. And so this would definitely, in my opinion, influence the capex. Whether the end users will be able or not to take on this cost or invest in this technology, I think it depends a bit on also what Eric was saying before. It depends a bit on the CO2 price and how much this resource and energy intensive industry will be pushed to increase the energy efficiency in their plant. For processes with in which the temperature is below 400 degrees Celsius, then we are going to compete with technologies that are probably also a bit cheaper, like could be the organic Rankine cycle, but maybe with but for processes with the temperature above the 400 degrees and up to 1000 degrees, then this is really, we're going to compete with steam technology, and the steam technology, they have limitation in terms of temperature. They have a lot of many other disadvantages that SCO2 power cycles could just offset. So it is difficult at the moment in this development phase to say exactly what could be the capex. This is an estimation, the one that I showed you here, but you can already see that according to the power output, the capex changes, and according also to the temperature. So I think a lot of factors needs to be taken into consideration, and also the integration in the processes.
Yeah, thank you, Ugo. I think we'll talk a lot during this program about this task that for us Baker Hughes, but also for the other company, I think could be quite crucial, together with the target on efficiency and the functionality of this plant.
Yeah.
Thank you.
Thanks to you for the question.
Just a question, sorry, from Eric from DGNR in the chat. He just wanted to know, what is the difference between turbo expander and turbine?
Okay,
Yeah.
so Eric, you mentioned this, right? So here we have one turbo machinery on the same shaft. We have a compressor and also a turbine, all on the same shaft. And here we have just one turbine, so one turbo expander, and so this will be connected fluidodynamically. But these are two different turbo machinery. Now this is the first concept that we have proposed. So in the proposal phase, now we want to add the same here as I mentioned. The cycle, it is not yet decided. Okay, so we have to, one of the tasks in the project will be to analyze the optimal cycle configuration. This one that you see in the slide is a recuperated cycle, but we are having internally a discussion whether this is really the optimal cycles based on the user needs. So yeah,
yes,
but
thank you. Thank you, Ugo. But it's just because I'm not an expert, and for me, a turbine is a kind of turbo expander. So I was wondering why there are two different terms to.
Okay, the turbine normally it's like blades that are hanged on a wheel, and the turbo expander normally is one single disc in which vanes are machines on it.
Oh yeah,
Maybe I
and
can
it may be radial
yeah.
or axial design. Is that the difference?
Normally, yes, that's to my. But of course here there are more turbo machinery experts. But so I.
Yeah, maybe I can support Hugo. Dieter from University Duisburg-Essen. Basically, it's the same. Yeah, you expand in a turbine or in a turbo expander the fluid, and then it's gonna rotate the rotor. So in many cases, axial turbines are just called turbines, and sometimes even companies call radial machines expanders, although some call them turbines. If you're not an expert, you can just remember it's the same.
Yeah.
Thank you.
You're welcome.
Okay. Yeah.
Any other questions? Or I didn't check the chat, but
Ugo, is the presentation available anywhere? There's a lot of material on but I can't read it on the screen.
So
thank you. Somebody responded already. Thank you.
Yeah.
Yeah, all the presentation will be available on the Flex website, and if the other project wants to point on the pages, there is no problem.
Okay.
So, is there any question for Fargo and Kurtwit's presentation? I want just to say thank you, Hugo, because it's quite difficult because the project began just a few weeks ago, and it's still difficult to present a project without some results or something like that. But the presentation was very clear, and thank you. And as I say, I think that the Culture project will bring some very interesting results and very good reflection about capex or some use of SCO2 cycle for waste heat. So thank you very much, Hugo. I don't know if there is some general question about all the presentation for today or something like that. So if there is no question, I will just let 5 minutes or maybe less to Dieter to speak about the next SCO2 conference. Dieter, are you okay or not?
Yeah, I don't need. I need.
I will
30
share
seconds,
the screen.
Yeah.
Okay.
Yeah, I don't need much. Just advertising again and again. Many knows from you knows that in 2023 we have again a 5th European conference. Many also involved. I think Brunel is involved, EDF, CVR, Delft, and many of you have participated in the 4th one. So we prepared already for the 5th one. And I think the date you need to remember is the conference date. It's in March 23. You can find this flyer also on the website, and the abstract submission date, 11th of July next year. So if you want to submit a paper, you can start working on it. We are ready to achieve it and would be happy for any recommendations how we structure the conference. It will be welcome. Yeah, thank you. And hope to see you in person in Prague again. This year it was online, planned in Prague, but in 23 it will be in Prague. That's my optimistic view on it. Thank you. I hope that was less than 30 seconds.
Yes, thank you, Dieter. And as if I can add, as Dieter said, you can see there is some conference topics because this is the most important topics, but we are very open on the organization committee about a new proposal or new type of new topics, maybe because we saw during the first years some topics like the SCO2 application or SCO2 loops were maybe less important than now. So I think that now we have a very dynamic, very productive project with good results, and we try to reach the market. Maybe some topics will take more importance. So don't hesitate if you have some question, because you already know there is the American Symposium and there is also this European Symposium. What we try is that to have an alternance between the two symposiums. So 1 year in US and 1 year in Europe. So you will be able to provide a very good paper to the both compared to the two symposium. Okay, and I don't have, I think we speak about the conference, so it's okay now. I don't know if there is another question about the different project. If there is no other question, I will just try to conclude very quick, and we will be on time. It's very precious now.
Paolo might have something, Albani, sorry.
Yes, Paolo.
Yes, thank you. I have a quick comment and a question probably for Professor Tasso. Yeah, we saw it's interesting to see that for heat recovery from industrial processes, supercritical CO2 cycle has application in large, medium size, like in the COOL-IT project we are developing together with ETN. It is starting right now. And in a small size application, as you mentioned, so 50 kilowatt. I had to disconnect for a while before, so I'm sorry if the question has been already made. I want to ask, 50 kilowatts in your opinion is a good size for commercial application, or it is just a demonstration and you think to a scale up of the iTherm SCO2 application?
Yeah, I mean, it was just for demonstration, really. It was the first attempt, but we didn't want to go too small.
Mm-hmm.
Let's say, I mean, because we did some work on 5 kilowatt before that, and the 5 kilowatt really is too small, particularly with the very low efficiencies, the heat transfer and so on. So then we thought that the 50 kilowatt system would give us a better idea of the performance of the heat exchangers and some idea of the performance of the turbomachinery. And also it was the cost side of it, because in effect we were a bit naive at that time in terms of the overall costs of the technologies that we were developing. So we did underestimate really the costs. But we think that now that we have built the demo facility, we feel that really the 50 kilowatt is the right size for experimentation. It gives you reasonable really quantities of heat transferred in the heat exchangers, and the cost is not too high to prohibit really testing of other heat exchangers. But also now with regards to the cool heat project, but also a national project we have, in effect, we are developing facilities to go down to 30 kilowatts and go to higher temperatures and pressures, particularly for heat exchanger, innovative heat exchanger research. So we are scaling down. Then we have the 50 kilowatt. But I mean, my personal ambition really is to go to 300 kilowatts.
So 300 kilowatt, you are thinking it's a good niche market to go against ORC.
Yeah.
So
yeah, that's right.
Yeah, it's interesting to see that supercritical CO2 cycle has a small application and mid-large scale application like in Coolit. So against the steam cycle and organic ranking cycle too.
Yeah, because I don't see, I mean, personally, really, I think the 300, because of the work we were doing in iTherm in terms of generally heat recovery, we identified that really, if you go to, if you have a heat recovery potential of 1 megawatt to 2 megawatt, then the market is huge. Because we also looked at the China market and so on. So really that range of market is quite huge. And therefore, really a machine of about 300 kilowatt, if you can make it economically, manufactured economically, then I think it can have a big potential because of the size. I mean, if you look at our heat exchanger that is 450 kilowatt, really is tiny. The microtube heat exchanger is tiny compared to other heat exchangers. So there really is no reason why really we cannot make a 300 kilowatt system very, very compact. And then we can, I think with the experience we are gaining both ourselves and other groups in Europe and of course in the USA, I think we can have a project really, perhaps it's something we can talk about really on that size of range really for mass application in areas where you have heat recovery potential of one megawatt or 2 megawatt. I think that's my kind of personal ambition.
Okay, a curiosity, if you can tell us, what are the size of the turbo machinery? So it's a kind of turbocharger, so it is very small for a 50 kilowatt.
Yeah, I think it's about it's 6 centimeters, I think.
Yeah, okay. Radial machine.
Yeah, it's a radial machine. Radial machine is about six sort of centimeters. So that's another one challenge. But really, the biggest challenge we have is on the inverter sides, which we shouldn't have, but at the moment we do have.
Thank you very much.
Thank you.
Okay, unless there are any further questions, we are now at 5. So Albani, I don't know if you want to have any concluding remarks.
Sorry. So sorry. So thank you to everyone. I don't have a remark. What I want to say just before is that I'm really enjoyed that there is a very great dynamic about sCO2 in Europe, and I really encourage to continue this communication between all the projects and all the different actors of the topic, and to try maybe to move on a common project or common demonstrator, because I think that now we are ready in Europe to have a demonstrator like there is in US, or there is in preparation in China. So I think that we have the capacity to work together in order to be able to propose also and to continue to work on these topics. So now it's 1 minute past 5. So we are on time. So I will just say thank you to everyone to be here today, to participate, for the presentation, for the question during the events. As my teams know, I not enjoy that it's an online event, but it's like that. So take care of you. And I hope that for the next month, we will be able to meet in face-to-face again during the another workshop or another conference or other meetings. So I will just thank you to all, and bye-bye to everyone, please.
Thank you. Bye.
Thank you.
Bye-bye.
Thank you.
Bye.
Thank you.
Thank you.
Thank
Thanks
you.
a
Bye
lot.
bye.
Thank you.
Totally.
Bye bye.
Bye-bye.
Bye.
Bye bye.
Bye.